Ooh, that looks like a complicated equation. Let's explain it. Just have one example here, shouldn't take too long. We're talking about free energy, the spontaneity of a reaction, the entropy change, the entropy change, delta S, the enthalpy change. We've also related the equilibrium constant to the free energy with this equation. If we wave our magic algebra wands and do some manipulation, it's not hard to combine those two to find this. And if I look at it in a certain way, it makes more sense. But let me not look at it graphically just for a second. Let me say, why does the equilibrium constant depend on temperature? We'll rewind the clock way back to several units ago where we talked about the rate of a forward reaction and the rate of a backward reaction, or the rate of a reaction and the equilibrium constants, and the rate laws associated with those. We, at some point at least, thought maybe exothermic versus endothermic reactions might go faster under certain conditions than others. So if I have an exothermic reaction, it might not go quite so fast in very, very hot environments, and vice versa for endothermic reactions. But this kind of gives us a hint about how temperature here and the equilibrium constant here, temperature here and the equilibrium constant here can be connected with the gas constant and the entropy, standard entropy of the reaction and the standard enthalpy of the reaction. Because we've been using those two to talk about free energy, and those look like the same, and so we equate that one and that one, and interesting. So, of course, we know most reactions go faster when they're warmer, and that does affect the equilibrium constant. I suppose the equilibrium constant goes larger as the temperature goes larger. Not always. So what if I were to graph it? Let's say this is the y-axis, the natural log of the equilibrium constant, and this is the x-axis, the reciprocal of the Kelvin temperature. Well, in the language of y equals mx plus b, then, like I had it shown up here, y equals mx, x is this x-axis plus b, the intercept. So we can look at it like this. So here's y equals mx plus b. And we can, well, first of all, I'm mentioning with kind of a frowny face here that delta H and delta S don't depend on temperature. That's not true. They do a little bit, but we're going to assume that they don't change much. Stuck a negative there. Must have made a mistake when I typed this up or whatever. So in any case, let's look at, so the slope is this negative delta H of reaction over gas constant term. I suppose the gas constant needs to be in units of energy to make the units of energy and the enthalpy to match up. But in any case, if I knew the slope, it would be a pretty simple matter to say, well, the slope is equal to this thing. And if I know the gas constant is a constant, I can just multiply both sides by the gas constant. So take the slope times the gas constant, and it turns out that 8.31 joules, that's the gas constant, times this rather large numerical value. The slope is in a negative direction. It's a large number of joules, but usually we express it in kilojoules. But still, 112 kilojoules is a fairly good chunk of change, if you want to say it that way. This is ponderous. I wonder. Well, delta H of reaction came out positive. I wonder if that's an endothermic reaction. I wonder if many reactions are exothermic, so what would happen to this slope if you called it an exothermic reaction? I don't think it would be positive. In any case, then if you knew the slope, actually, if I do a linear regression on some kind of graphing calculator or software program, I find the slope and the intercept tells me this term. So instead of the delta H information, it gives me the delta S information. So what if my slope was, say, for example, negative 14.51 on this scale, whatever that is? Then wouldn't it be a simple matter just to take that negative 14.51, that's the intercept, and say it must be equal to the entropy change divided by the gas constant. Take both sides times R, Again in energy units, and this is in joules, not kilojoules. So that's interesting. Joules, kilojoules. This one came out to be in kilojoules. Excuse me, just a very large number. I had my gas constant in joules per mole Kelvin in both cases, but whatever. Okay, well, that's all I had for that one. So, let me see. What's the relative importance of this equation? Overall, it's very important. Will you be asked to use it on the exam? I can't say. Let's see if it crops up in other lecture questions, or perhaps discussion, or perhaps homework. I don't know. It's good to practice, that's for sure. Good to think about how temperature and the equilibrium constant are related, or the temperature affects the equilibrium constant. That's good to think about. Thanks, guys.